Good evening. Today we are going into the next part of our chapter, mechanical properties of fluids, and today we are discussing viscosity. Now, you might have noticed that every fluid offers some resistance to motion. For example, suppose you take two jars, and in one jar we have a very thick viscous fluid like honey or let's say oil, and in another jar we just have water. And if you allow two metal balls to fall through the two jars, you will see that the metal ball will fall faster in the liquid water than it would in honey or oil. And this means that there is resistance to the movement of this metal ball inside. The resistance offered is different in different fluids. So this resistance to fluid motion, which is like internal friction between the layers of a fluid, is what you call as viscosity. Now here what I've shown you here is two glass plates. We have an upper glass plate and a lower glass plate, and in between this glass plate, which is having a distance between the two glass plates is L, we have a highly viscous fluid. Let's take honey, or like I told you, oil, in between the two glass plates. Now this glass plate, the bottom one is fixed, stationary, but you're applying a force on the upper plate and pulling it to the right, so that this plate moves with a velocity v, uniform velocity v, but this plate is kept fixed. So naturally what will happen is, this layer of this fluid in contact with this plate will also move with the same velocity v, but the layer which is in contact with the stationary plate will remain stationary because that plate is fixed, and because of that internal friction, that layer in contact with the glass plate on the bottom will remain stationary. If you take any other liquid layer in between, you will see that the layer above it will pull it to the right with a velocity v, but the layer below it will pull it backwards because of what we have as this internal friction. And therefore you see that the velocity of the layers will increase as we increase from 0 to v as we go from the bottom to the top glass plate. Now, like we did in properties of fluids, properties of solids, remember we discussed about the shear strain. The shear strain is when the upper plate or the upper surface moves with respect to the lower surface. Let's say the displacement is through a distance delta x, and if this is L, then I hope you remember, the shear strain is delta x by L. Now in the case of fluid, what happens is, the fluid is continuously flowing. So it's not enough for, unlike a solid. In a solid, this will stop. After some time, this will be a constant value. But a fluid is continuously flowing, and therefore the strain, the delta x, will go on increasing with time. And therefore it's important not to just discuss the shear strain, but to talk about the shear strain rate, which is the shear strain in unit time, which means you will have a delta x by L divided by this delta t, which is delta x by delta t is the velocity, so that is v by L, the shear strain rate. So if you look at this picture here, at some instant initially we have the fluid portion A, B, C, D being now, because of the force applied, the upper layer starts moving but the lower layer remains fixed. And so at some other instant, after a time delta t, you will see that the upper face has moved through a distance delta x, and therefore you will have the same portion of fluid represented by A, E, F, D. So that's what I've shown here. At some instant, we have the portion of fluid A, B, C, D. After some time delta t, because of the shear force you have applied here, the shear stress that you have applied, this upper portion moves with respect to the lower one, and that portion now is represented by A, E, F, D. So we now have the coefficient of viscosity, eta, defined as the shear stress by the shear strain rate. So coefficient of viscosity eta is defined as a ratio of the shear stress to the shear strain rate. Shear stress, we know from properties of fluids, is F by A, and the shear strain rate we know is L by V. So we have this as FL by AV, which is the coefficient of viscosity. Also, its SI unit is Poisson. The other units are Newton second by meter square, or Newton per meter square is Pascal. So we have Pascal second also as its other units, SI unit. Then the dimensional formula for this you have learned in the first chapter, units and dimensions, ml raised to minus 1, t raised to minus 1. It's also important to note that, see, highly viscous fluids like honey, if it's a liquid, if you increase the temperature, its viscosity decreases. But in the case of gases, if you increase the temperature, its viscosity also increases. So this is what we discussed under viscosity. We now go on to discuss the Stokes law. In Stokes law, what we have is, let's say we have a jar or a container having some highly viscous fluid, okay, and you allow an object, let's say a metal sphere of radius a, to fall through it. So we have a container with some viscous fluid in it, and you're allowing a metal ball, a spherical ball made of metal, to fall through it. Let this have a radius a. This metal ball has a radius a. Now this, as it falls through the fluid, we know that it is going to experience a viscous force, a viscous drag, which is going to oppose its motion. So if it's moving down, the viscous force is going to act in the upward direction, because it is like internal friction opposing the motion of that object through the fluid. So this viscous force, which I call Fv, is found to depend on three factors. The first one being the coefficient of viscosity eta of this liquid. Greater the coefficient of viscosity, greater will be the viscous force. The second thing is the radius of that metal ball, or radius of that object or sphere. The third is the velocity with which it is falling. So it's falling down with some velocity through the fluid, and so the third factor is the velocity of the object. Okay. Now using dimensional analysis, we can actually find out an equation that relates the viscous drag or viscous force to these factors. So let us try to derive an expression for that viscous force. So this viscous force is found to be directly proportional to coefficient of viscosity, the radius of the sphere, and the velocity. So this is raised to a, b, and c. Or we may write the coefficient, the constant here, the constant of proportionality here is determined to be 6 pi eta raised to a, the radius raised to b, and velocity raised to c. The dimensional formula for force, as you know, is mlt raised to minus 2. This is equal to 6 pi. Eta, we just know, I told you, is ml raised to minus 1, t raised to minus 1 raised to a. And then we have the radius, which is simply L raised to B. Then velocity is LT raised to minus 1 raised to C. So if I combine all the M is raised to A, L is, here we have a minus A, here we have a plus B, and here we have a minus C. And then we have T raised to minus A, and here we have a minus C. Now if you equate the, this is raised to 1 and 2. So we have our equations where A is equal to 1 when I compare these two. By principle of homogeneity, we know that it should be the same. The dimensional powers must be the same. So we have minus A plus B minus C equal to 1, and minus A minus C equal to minus 2. If you solve this, you will see A is equal to 1, B is also equal to 1, C is also equal to 1, which means we have our equation for F as 6 pi eta AV, where eta is the coefficient of viscosity of the fluid, A is the radius of that metal sphere that is falling through the fluid, and v is the velocity with which it is falling. So this is what you call as the viscous force given by Stokes' law. This is Stokes' law. Stokes' law. Okay. The next topic that we are going to discuss is the terminal velocity, where we are going to use this Stokes' law or expression for viscous force. So we are going to discuss terminal velocity. Now let me first of all try and explain to you what is this terminal velocity. So here in this case, we have this liquid or fluid of density sigma, but this sphere has a radius a and density, it's made of a metal of density rho. Now as the sphere falls through this fluid, there are three forces acting on it. First of all, its weight mg acting in the downward direction. Then there is a viscous force which we discuss now will be opposing its motion in the upward direction. There's also what we call as the buoyant force. Whenever we have an object inside a fluid, there is an upward force acting on it called as the buoyant force. Now if I write expressions for these three, the first one, let me give the heading, terminal velocity. Okay, so the first one is the weight of that body, the metal sphere, m into g. I'll write it down there. The weight of sphere. That's the force acting in the downward direction, which is m into g. Mass we know is volume into density of the sphere is, I said rho into g. Volume, it's a sphere, so 4 by 3 pi. Radius is a cube, rho into g, which is my first equation. Then there is viscous force, which is Fv, we just saw, that is equal to 6 pi eta A into V, second equation, where eta is the coefficient of viscosity, A is the radius of the sphere, V is the velocity with which it is falling. And we also have the third one, the buoyant force, given by Archimedes, which principle, which says that the buoyant force on a body is equal to the weight of the fluid displaced. So weight of fluid displaced, which is again mass of the fluid into g, which is volume into density of the fluid we know is sigma into g. Volume displaced will be the same as the volume of the sphere. When a sphere is immersed in this fluid, the volume of fluid displaced will be the same as the volume of that sphere. So this will be 4 by 3 pi a cube sigma into g, equation 3. Now you see what happens here is this 4 by 3 pi a cube rho g, the whole thing is a constant, because a is the radius, rho is the density, g is also a constant. You look at this 4 by 3 pi a cube sigma g is also a constant, right? Because sigma is the density of the fluid, a is the radius of the sphere, and g is also another constant. So we have our mg and buoyant force remaining a constant. But Fv is not a constant because it depends on the velocity. And you know, velocity of a falling body, freely falling body, is given by root of 2gh. So as h increases, the velocity of that body is going on increasing, and as the velocity increases, the force, viscous force, goes on increasing. So now for this one, the downward force is mg must be equal to the upward force, that is buoyant force, plus the viscous force. Now this and this being constant, as this goes on increasing, at some point what will happen is the sum of Fb and Fv will become equal to the weight which is bringing it down, the mg. So then what happens is the sum of the upward forces becomes equal to the downward weight that is bringing it down. So the net external force on this body becomes 0 because the upward force is balancing the weight. So when the net force on that body becomes 0, you know, force is mass into acceleration. Acceleration of the body becomes 0. Acceleration 0 would mean that the body is moving in the downward direction. So by Newton's first law, it will continue in its movement in the downward direction. But now it will move with a constant velocity because acceleration has become 0. Net force is 0. So now it will move down with a constant velocity, and that constant velocity is what you call as terminal velocity, denoted by Vt, terminal velocity. So we are going to find out an expression for that terminal velocity Vt. So what we can do is, we can equate the three equations. I just told you now that when the body starts moving with a constant velocity Vt, the terminal velocity, we know that the downward force, that is the mg, bringing it down, has become equal to the sum of the upward forces. Or this was 4 by 3 pi a cube rho into g equal to, this was 4 by 3 pi a cube sigma into g plus 6 pi eta a into v, which is called the terminal velocity Vt. And we need to find an expression for this Vt. Pi being common, I'll cancel everywhere. A, this will become square, this is square, and I cancel this here. So I'm going to bring this to the left hand side. So we have 4 by 3 a square rho bracket, bracket rho, no, g rho minus sigma must be equal to 6 eta Vt. Or I may write, so this 6 I'll cancel with here. So this is 2 and this is a 3. So we have the terminal velocity equal to 2 by 9 a squared g into rho minus sigma by eta. So I brought this eta also down. So we have our expression for the terminal velocity, 2 by 9 a squared g rho minus sigma by eta, where a, as you know, is the radius of the sphere, g is 9.8 meter per second square, rho is the density of that metal ball, sigma is the density of that fluid, and eta is the coefficient of viscosity of the fluid. So this is the expression for the constant velocity with which the body is going to now fall down, called as the terminal velocity. Thank you.